I believe we have a demo now of the wonderful power of...
Well, so it's a demo of how, of a small subset of... I don't know how to do that. Control Shift plus, you think that'll work? Oh, it's Emacs. No, it's not Emacs. It's a movie. I can try Control Shift plus if you want. Oh. So no, it's a recording. It's a movie. So I'm going to show you how typical work with SICL happens on a daily basis. And because this is a movie, I can just pause it with a space bar here. So if you see something that you don't know what it does, then let me know. And this is done on my very slow desktop. So I start by using ASDF load system on the host, which in this case is SPCL. And then I do an in-package SICL boot, and I start the bootstrapping script. And if you see here, what happens first, it fills up environment S0 with lots of macros. And the way it does that, it starts by manually defining def macro by saying setf macro function of def macro to lambda such and such. So that's illegal because it's a host. It's compiled by a host compiler, and so it will do the wrong thing if you have the wrong scope and so forth. So then it defines def macro using the defined def macro, which is fine, and then it does it a second time in order to get SICL code to be executed when def macro is used. And so then the rest of the macros kind of follow here. So we have all kinds of macros loaded up initially. It's 3 times as fast on my new laptop, kindly given to me by my wife. Yes?
So it was doing a whole lot of stuff into E0, then suddenly at some point it changed to E2 and E3.
Yeah.
E2's gone away. What are these E things?
Each E is a first-class global environment. E0 is dedicated to macros. E1 doesn't play any big role, I think. E2 contains host objects mainly. E3 contains what's known as bridge objects, which are host objects but that represent SICL objects in a very strange kind of way. And then E4 and E5 are what I call ersatz objects. That is, they are SICL objects represented as a header and a rack and a pointer to a class and so forth. So it's a direct mapping to the way it will look in native code. So that's very technical. I presented that in a paper, and I don't have time to go through it again. But it basically executes the same mop or CLOS code to create all the hierarchy of all the classes and all the generic functions that are defined by the mop and by the common Lisp standard. But it does this 3 times. It does this first in the host and creates host objects. And then it does it using the first code in order to create bridge objects. And then it uses the bridge objects to create ersatz objects. And then in E5, it kind of creates because now the classes of objects in this environment are in that environment. So the last step is that it creates a circular structure. So like I said, this is roughly 3 times as slow as, they're having it 3 times as slow, yeah. So now, what does it do here? Well, this is still SICL-specific code here. Initialize instance, make instance, slot value, method combinations, compute applicable methods, so that's all MOP stuff. Computing discriminating functions. And then, let's see. Yeah, it just continues. It's in E4 now, so it should be starting to do ersatz objects. Now it's in E5. So it just does it all over again in order to get the right representation in the final phase.
Your environment names are not as beautiful as your module names.
Thank you. This will change because they're going to have names now that reflect the kind of module that would be compiled in it. So this sequence doesn't work to the end. So now we call satiation. Satiation takes a very long time because it traverses all the classes of the system, tries to compile effective methods, and if it can, and it combines them. Now we're getting to code generation, and that's all the warnings that you see here that the Haley is responsible for. It's because we don't know how to do multiple values beyond 5 or something like that. And now things are getting interesting here because we were starting to load external modules like Inkless and Claustrum, Alexandria. Alexandria is a prerequisite for eclector. This is Truckler, C-type, canonical type is what it means, C-type, canonicalized, which Baker says is too costly, which is why he didn't do it. And this is what?
Did you find it costly?
We had no choice, basically. And I didn't do it. It was Alex Wood who did it. Seems to work fine. So this is eclector. Many of the warnings that you see are due to the fact that we use load eval semantics rather than compile. This is loop, it's loading now. Now it's loading code utility so that it can prepare for loading cleaver, but we don't load cleaver yet. Random, Claustrum, format.
Where did your random come from?
I forget who wrote that. I probably forgot. Forgot to include that person. Who wrote random? Okay, so now it becomes interesting. This finished bootstrapping in 200 seconds. It takes 80 seconds on my new laptop. And we can see here, we have these environments E0 to E5. We can call Cluzo. Cluzo is the inspector distributed with McClim. It's another Jan Moingen product. It used to be mine, but he took it to completely different heights. So we can inspect a first-class environment, and we can get the hash table and see what's in it and so forth. So actually, a lot of the SICL code has been executed in the host, but not as native code. Okay, so these are just the variables. And now let's do something interesting here. This is executing Claustrum code here. And find class and client E5 standard object. That's the protocol used by the first class environments. So it finds standard object. in E5. And as you can see, it presents itself as header. And everything in SICL, when it's an ersatz object, it presents itself as header in the host. So it's completely undebuggable. We can inspect it with Cluzo. We can see here that it has what I call a rack. You can see the name of the class here, standard object. We can inspect its class. This is the class objects that we're inspecting here, and we can take the rack of that and its standard class. So we can work like that. Not ideal. Try to do more printing during debugging time, but if printing goes wrong for some reason, then everything just goes to crap. So it's usually better to avoid too much sophistication. We can actually run a read-eval print loop in any of the environments here, and this is E5. You can see I would get a double greater to distinguish it from something else. I can do things that work, simple things, def generic FF, def class A, def class B inherits from A, define a method on FF specialized to B, define a method on FF specialized to cons. I can call FF, and what I'm going to do now is I'm going to call FF on something for which it doesn't have a method. And as it turns out, no applicable method is caught by the host. So you're going to get an SBCL error. So this is what it looks like when you get an SBCL error. But it's not lost, because I can go to a frame that has been executed as SICL code, and I can call the BT function in SICL. And in fact, I get a backtrace inspector implemented in CLIM that shows the call stack of the SICL code here. And I can click on a stack frame, and I can get source information. So this is how source information works in the CST. And it's propagated through the compilation process. And I directly get the offending expression, or the offending form in red. So this is quite comfortable for a bootstrapping environment. I don't know if you understand that, but as opposed to core dump and then GDB or something like that. So even if the error is caught by the host, I'm not completely stuck. And there are some frames without source information, probably because they were executed by the host. But I can still get the, this shows that I was able to click on one of the arguments that just said header up there, one of the arguments to that stack frame. And it then starts Cluzo on that object. So I can inspect which argument that was. And so it's the same thing as before. It can just, this is the function FF. Nothing particularly interesting. This is a stack frame without source information. It's still FF. So let's get out of that. And now I got out of the REPL, so I need to get back into the REPL. And I can use type P. Here is something that works. We can type P make instance quote B is of type A. Yeah, sure. And I'm going to do something that does not work, but this time it's going to be caught by the SICL condition system, and it looks a little bit different. Quote hello is not a known type, so then I get directly into the backtrace inspector. It was called by the SICL condition system. And I can again get source information on the right there and see exactly what happened. So that's kind of a sample of how my daily work looks. You know, bootstrap, SICL code, get an error of some kind, use the tools in order to figure out what the problem is, fix it, redo, so forth. So I guess that's pretty much it.
Questions, comments?
But you used ASDF to load Clevier, so
Yeah.
if you change just one source file, you can just call the same ASDF load form again to continue with that file and only the ones afterwards, right?
Right. So ASDF is used in two different ways. The first thing you saw was ASDF executed by the host, SBCL, just to load the source code of bootstrapping, essentially. So I didn't do anything to make that work. That's just SBCL code. But then I taught ASDF to load systems into first-class environments using the Cleaver-based compiler. And so what you saw in the last phases of bootstrapping was that I used ASDF to load things like IncLS, to load things like what was called Alexandria, and so forth. And that needs to change because now it uses load semantics, and I need to go file compilation semantics. But I know how to do that with ASDF, so that's not a big deal. So yes, you are right. I could do that. But this is bootstrapping, so if things go wrong, there is something seriously wrong, and you usually have to do it from the beginning.
You demonstrated the bootstrapping using SBCL. Would that also work with CCL, for example? Or whatever complete Lisp implementation?
There are probably cases where it will not work, but that would be unintentional on my part. So it's meant to work, and I just haven't tested it. But we've run into various strange things. In the beginning, we translated abstract syntax trees back to SBCL source code, and then we compiled that, and the SBCL compiler just croaked on it. It just couldn't handle it. It was too big. And then we ran out of immobile space in SBCL. So there are limitations of particular implementations that we will run into because we use a lot of the resources of the implementation. So I cannot predict that, but I haven't tried it.
I would like to know, what are the funniest things or most surprising things that you learned in this venture?
Wow.
There's funny things that happen.
Maybe how little I knew from the start. The learning experience has been absolutely fantastic, so it's been great.
More questions, anyone? Okay, again, Robert, thanks very much. It's really a pleasure to listen to you. And I learn a lot, and I'm challenged a lot every time I take the time to listen to one of your presentations. So thanks again.